Today's topic is axial tension and compression. We'll go through 3 statically determinate examples. This is third example. A rod permanently fixed at end C is loaded as shown in the figure. Determine the inner diameter of the hole that can be drilled axially in the rod to a depth of 3 meters if the maximum displacement of the rod Umax is equal to 0.15 millimeters. Given is force P 15 kN, Young's modulus, and the outer diameter, big D. And the condition, maximum displacement 0.15 millimeters. And we need to calculate small d, that is the inner diameter of the hole. Well, so we need to think. The maximum displacement is to be 0.15 millimeters. The displacement of cross-section B it's the elongation of part BC. Delta LBC is the displacement of cross-section B. The displacement of cross-section A is the sum of these two elongations. So UB is delta LBC and UA is delta LBC plus delta LAB. And we write out the forces in these sections. The force in section AB, looking from the right side, is 3P. The force in section BC, we now see two forces. It's 3P minus P, so 2P. Well, and due to the fact that both in section AB and in section BC, these forces are positive, well, there will be elongation. Both of section AB and elongation of section BC. So the maximum displacement will be the displacement of point A. Because both in one and in the other section there are elongations. So the maximum displacement will be where there will be the sum of these elongations. It would be different if, for example, the force in section BC was negative. Then we would have to think about it. But here we have both elongations will be positive, so the maximum displacement will be the displacement of the end of the rod. Well, this results from the formula for elongation, and from the sign of force in the rod section. If it's positive, it's elongation. If it's negative, it's shortening. So this will be Umax displacement of cross-section A. Well, so let's write out, we can write out the length AB, section AB, length of section BC. Well, and now also the cross-sectional area. Here, I wrote out the cross-sectional area AB. It's pi d squared fourths. That is simply the area of this circle, which is the cross-section. Well, and now the cross-sectional area, BC. It looks like this cross-section. So we're interested in the area of this ring. Well, the area of the ring will be pi big D squared fourths. From the large, we calculate the area of the ring. From the large circle, we subtract the small one, and we have the area of the ring. So pi big D squared fourths minus pi small d squared fourths. We can factor out pi fourths and write it this way. And now to the conditions of the task content, that is maximum displacement 0.15 millimeters. I converted it here to meters because I'll substitute everything in basic units. And the maximum displacement is the displacement in cross-section A, that is delta LBC plus delta LAB. So this is to be equal to Umax, that is 0.15 times 10 to the minus third meters. Well, and we substitute. Delta LBC, that is force. Here I did it in reverse. First is delta LAB, and then is delta LBC. Delta lab is the force in the rod in section AB 3P times the length of the section 2 meters divided by Young's modulus and cross-sectional area, PID squared fourths. And we add the same with section BC. And this is to be, the maximum displacement of 0.15. Well, so this displacement is to be less than or equal to 0.15 times 10 to the minus third. Well, and we need to transform this. By multiplying by the inverse of this denominator and this 4 jumps up to the numerator for us. And immediately we multiply by e times pi, so here in these fractions it will disappear. It will appear on the right side. We multiply now by this denominator to cancel out. That is by d squared big minus d squared small. This bracket appears for us at each component. Well, and we multiply out these brackets. We get quite a lot here. Well, we simply multiply. I won't add unnecessary commentary here. D squared cancels out for us here, and we can already substitute numerical values at this point. So p thought from the task content 15 kN, Young's modulus 85 GPa, large diameter d 0.2 m, and everything, I now substitute all this into this inequality. Of course, in basic units. And I canceled out here, well, mathematical transformations. Now we need to calculate the small diameter. So we move to one side. To the right, we factor out what stands next to the unknown and divide by this bracket. We have that d squared must be greater than or equal to some fraction. Square root, of course. And we calculate the specific value. The diameter must be greater than or equal to 168 thousandths of a meter. We can write it as centimeters, so multiply by 100. Move the decimal point 2 places 2 times to the right, and we have that the diameter must be greater than or equal to 16.8 centimeters. So we have dimensioned the diameter of this drilled hole. That's what they asked for. We can estimate here if it makes sense. Well, the large diameter was 20 centimeters. Well, it's possible that the small diameter can be as much as we calculated. Well, if we got above 20 centimeters, we can immediately say that, well, nonsense, we calculated wrong. So this is our result, and that's all on this topic. If you have any questions about the solved tasks, I encourage you to ask questions under the video. I'll try to answer. I also recommend our other productions. And that's all. Goodbye. Greetings. Bye.